we left off in numerics of the bundle adjustment. Remember, the idea of bundle adjustment was to jointly estimate camera motion and three. Is this too loud? It's okay. Okay, to jointly estimate camera motion and 3D structure by minimizing a loss function. Let me go back to just recap what the loss function is. These were the pioneers who developed it, these ideas, and you remember in particular the first computerized solutions were developed by Helmut Schmidt, who came from Germany, in fact in the team of the rocket engineer Wernher von Braun, who went to the US to develop rockets and spacecraft. And in his team, Helmut Schmidt was part of the team, and he brought all the bundle adjustment knowledge, and he teamed up with Dwayne Brown to deploy things on big supercomputers. Well, of the times, right? And the loss functions that people minimize is, this one, where you basically say you are observing a set of points in a set of images, so n points in m images, and for each point in each image you want to make sure that the observed point is close to where it should be based on the perspective projection of the 3D point xj with rigid body motion ri and ti. And then you penalize the quadratic discrepancy. I already mentioned that there's many parameters that we try to estimate here. Basically 3 parameters for every 3D point, so that's 3n parameters, 3 times n parameters, and then 6 parameters for the rigid body motion of each camera, that's 6 times little m here, plus 3 times large n, that's the number of unknowns, and then we have a large number of observations. How many? Basically, ideally, we have m times n unknowns. Observations. This is often important. You know, this is not a linear equation system that we're solving here. It's a nonlinear optimization problem. But still, it's often useful to look at how many observations do we have to constrain our solution compared to the number of unknowns. And you can see that with more points and more images, the number of observations grows faster than the number of unknowns, because it's n times m here. Right, so this is a useful observation. So in some sense, the more images I have of the world, the better I can constrain the reconstruction problem. That's the bundle adjustment problem. Now we started talking about iterative solvers to solve these so-called nonlinear least squares problems. If we go back to the loss function again, look at the loss function. You know, when you work in this field, you tend to see a lot of energies, a lot of loss functions, and with time you start to see what is there. There's typically a summation over observations of images and points, and then there is a loss function that has a square here. So on the outer surface it looks like it's quadratic in the unknowns, but be careful, the unknowns are in here. And this is a rigid body motion of the point xj and then the perspective projection. And as you remember, this is not a linear transformation, which means the residuals that we square here, the residuals themselves are not linear, and hence the loss function is not quadratic. And this is the class of problems that is called nonlinear least squares, because the residual is not linear and we have a least squares problem. And so if you write this more compactly, you can write these residuals as Ri squared here, squared residuals, summed over I, right? So the summation over I would be the number of images times the number of points. So that's the number of terms in the summation. And then we have all these residuals that depend on our vector of unknowns x. So this is often useful to reduce the loss function into a compact form so that you see what is the structure of it. Some residual that depends on the unknowns x, rotations, translations, and the 3D points, and then squared and summed up, right? And so for this type of loss function, nonlinear least squares, a very powerful and popular technique is an approximation of the Newton method called the Gauss-Newton method. This was the Newton method. We have to, the update basically says, take the old estimate minus the gradient multiplied by the inverse Hessian matrix. So this is the classical prototypical second-order optimization method. And you remember the idea of the Newton method was that we take our loss function, whatever it is, we fit a paraboloid to it. Oh, there's only one color here. So basically we start somewhere, we fit a paraboloid, and we step always to the minimum of the paraboloid. And once we do that, this is the update step that you can derive. And now comes the key idea of the Gauss-Newton method. It says if we compute the Hessian for this sum of squared residuals, we first have to compute the first derivative. So we do the chain rule, right? If we derive this with respect to r, with respect to x, we first get ri, then times the ri by the xj. And now if we apply another derivative in order to get the second derivative matrix, the so-called Hessian, we have two terms based on the product rule. Derivative of the first times the second, that would be this term, and then derivative of the second times the first, that would be this term. And so you see we have a product of two first derivatives of the residual plus the residual times the second derivative of the residual. And now, so this is the exact Hessian for the Gauss-Newton, for the Newton method. And you could just take that and plug it in here, compute the update. But what you can also do is, and this is the idea of the Gauss-Newton approximation, is you drop this second term. Basically saying we assume that the residuals are essentially linear. And so this term is larger than that term. And then this term dominates. So if your residuals are near linear, then this term will dominate this whole expression. And so we can basically just take this first term where the Jacobian is the matrix of the derivatives of the residual. And so this is the Gauss-Newton approximation. The nice thing about it is a second-order method because it uses a second derivative of the loss function, but an approximation of the second derivative which is such that you actually, with respect to the residuals, only need first-order derivatives. And so you could say it's kind of a hybrid between a second order and a first order method, but it is considered a second order method because it uses an approximation of the second derivatives. But computationally it's just more efficient because you don't have to compute the full-blown Hessian matrix. For big problems, we're talking millions of points, plus thousands of camera transformation parameters, this is a matrix that will be million times a million, right? Good luck with setting it up and inverting it, right? I'm sure you haven't spent much of your career so far inverting matrices, but this is one big thing, and it's a big problem. And so if you can avoid inverting a matrix, then obviously this is something you'd want to do. And we'll come to that. So this is the Gauss-Newton algorithm that we derived. And then we talked about the Levenberg-Marquardt algorithm, which is a variant of the Gauss-Newton that includes a damping. You can damp the original Newton method. It basically means you add a little bit of the identity to the Hessian matrix, that you can also see it from a numerical perspective that stabilizes the inversion of the Hessian matrix, because the identity matrix is always easy to invert. And more specifically, it becomes something that is a hybrid between the Newton and the gradient descent. If you set lambda equals 0, you have the original Newton method. If you let lambda go very large, then essentially you can ignore the Hessian here. This term will dominate for large values of lambda. And then you have essentially a gradient descent with step size 1 over lambda. And so the idea is, if you have a loss function like here, that initially, when you're in a regime maybe where the quadratic approximation is not good, you would do gradient steps, and once you reach a regime where the quadratic approximation is better, you can switch to a Newton method, and you can do that transition gradually if you want. The key challenge obviously being, how do you pick lambda, how do you update it in a meaningful way. This is a whole art by itself, much like just the step size selection in gradient descent is a bit of an art. There was a question there.
Why does gradient descent help in concave situations?
You have to see, if you're in a concave situation, then the Newton method doesn't actually apply. Because then if you fit a paraboloid like this, it's going to be a paraboloid that's open to the bottom. And then if you say, can you find the minimum of that paraboloid? It doesn't have a minimum. So the Newton method isn't even applicable in concave situations, right? So this is a little bit the issue, that the Newton method assumes that you're in the basin of attraction, and then it goes fast to the minimum. But you have to first get to that basin, and this is where the gradient descent will help you. As I mentioned, Leeuwenberg in 1944 and then Marquardt in 1963 devised damped versions of the Gauss-Newton method. So here the Gauss-Newton approximation, J transpose J as an approximation of the Hessian, where J is the Jacobian, the first derivatives of the residual. And then you add again this damping term to this approximate Hessian. And then multiply by the gradient. This is then J transpose R, right? The gradient, we had it here. For these residuals, you can write it as R times the Jacobian. This is the Jacobian transpose times R. And so this is the Leeuwenberg damping, just a plain, vanilla damping, an isotropic damping, meaning you damp the same in all spatial directions. And what Marquardt found, that in some cases it's more suitable if you have these, in 2 dimensions loss functions that have kind of a more anisotropic nature with isolines like that. You don't want to end up doing gradient descent, and you don't want to oscillate too much. And then you want to take larger steps in the flat directions and smaller steps in the more curved direction. And you can do that by having this weighted diagonal, where you basically weight it by the curvature in each direction. That is the Leeuwenberg-Marquardt, but as I mentioned, which one you choose, the Gauss-Newton, the Leeuwenberg-Marquardt, it kind of depends on the problems you're solving. And it's not always this super adaptive Leeuwenberg-Marquardt that's going to work best. We had papers where, my students say they prefer the just plain old Gauss-Newton. So it depends. But all these algorithms are being used for solving the bundle adjustment problem. Let's look at this more specifically. Here is the bundle adjustment problem. This is the sum of residuals squared. Here I write it like that. And then x is the number, here now is the vector that contains the parameters involving the xp stands for the poses, that means rotation and translation of the camera. So that's 6 parameters for every image. And XL are the so-called landmark parameters. The landmarks are the 3D positions of each point. Right? And so this is a long vector that is 6 times little m if m is the number of images, and 3 times large n if n is the number of points. And the Gauss-Newton algorithm can be derived from this loss function in a slightly different way. You can say, and it comes out to the same really, you can say approximate the residual with the first order Taylor approximation, where you have the initial residual at and then plus the derivative j is the derivative of r with respect to x times delta x, that is the update. So this is a linearization of the residuals that we do here. Right? So they're nonlinear, but we linearize it with a Taylor approximation, and then we have an update, so the change in our unknowns delta x. And now we try to find an update in the parameters for the cameras and the parameters for the 3D points, delta xp and delta xl. And once you insert this linearization in this loss function, you get this expression here with the residual R0 plus then the Jacobians in the camera poses and the landmarks times delta xp, delta xl squared. And if in addition you add this damping that we had in the Levenberg method or the Levenberg-Marquardt, you add basically a regularizer that says that I don't want to the updates shouldn't get too large. So much like in gradient descent, you want to stay close to the initial estimates. And you can check for yourself, but if you take this loss function, you can see by construction, since I linearized the residual, this loss function becomes quadratic, and the regularizer on the updates is also quadratic. This whole problem becomes quadratic in the updates delta xp and delta xl. And if you do these updates, you get basically to the Gauss-Newton or the Levenberg-Marquardt algorithm. And this is another way to derive the Gauss-Newton and the Levenberg-Marquardt, that you approximate the loss function and then apply an optimization method. So based on this linearization, we have a quadratic loss in the updates of the camera poses and the landmarks. And this we want to minimize, right? And once you have a quadratic loss function, the minimality condition is a linear equation system of this form with some matrix of like this one, and then the updates in landmarks and poses of the camera, and then some constant vector b. And all of these can be computed, and then you can compute the update vector delta x and delta xp and delta xl by inverting this matrix. And this matrix, this equation is called the normal equation, and this matrix is called the system matrix. So you can see all these things have names, indicates that they're just being used quite a lot. Yes? Yes, these are damping matrices. That relates very much to this term here. So you could use, this diagonal Jacobian if you of J transpose J, but you can use any kind of damping matrix that basically tells you how you want to damp the updates. And so this is the normal equation, and what we do is we solve this equation in order to determine updates for the parameters for the camera pose and the parameters for the landmarks. So far so good. The key problem is that this matrix, we mentioned it before, it's huge. 1,000,000 times 1,000,000. So don't try to do this at home to invert such a matrix. How do we go about it? What's interesting, and this is something people studied this matrix intensively and looked at what is the structure of this matrix. And what they find is that it has this structure. So U is a fairly small block. Why is it small? U is the block that contains the number of camera parameters times the number of camera parameters. And typically you have far fewer parameters for the cameras because you're going to have maybe 100 images times 6 is 600 camera parameters. But then you're going to have 1,000,000 points times 3 is 3,000,000 point parameters. So whereas U is only like 100 by 100, this ordered 100 times 100, the V matrix is more like 1,000,000 times 1,000,000. So U is fairly small, but V is gigantic. But what's nice about V is that matrix is essentially block diagonal. And this is what you see here. This big thing on the bottom right is a matrix. This is from actual bundle adjustment problems from Lurak is an example. And what's visualized here graphically is the black elements are the non-zero elements. And the white elements are all zero. Why is there so much zero in V? Well, basically, V involves the 3D coordinates of the points, and the points will typically not all be visible in all images. If you walk around with your camera, you will have sets of points in certain images, and only if multiple points arise in the same image, they share the same residuals, then you will have an element, but typically they will be uncorrelated. Yes, was there a question? Yes, I added that last night. It's in this, so because I think it's important for you to understand what this matrix looks like, so I decided to add this. Is a new slide, but the slide deck is online and it contains the new slide. So if you want to go and download it, you'll find it. It should be in the new slide deck. If it's not, let me know. Interestingly, you can go back to the works of this Dwayne Brown that I mentioned, this guy bottom left, and you find papers of his from the 50s. And these papers, he studies very intensively the structure of this system matrix. He looks at it, this block diagonal structure, and you could say he dedicated years of his life studying the structure of these matrices, and a lot of researchers did, because if you have a big matrix and you know you need to invert this matrix, just plugging it into MATLAB or something and say invert it, that's not going to work, right? It's millions by millions. So you have to really look into the details and see, isn't there something in the structure of these matrices that I can exploit? And indeed, it turns out there is, since this big matrix V here is essentially diagonal, it's very easy to invert. Diagonal matrices or block diagonal matrices that just have elements around the main diagonals, these are very fast to invert. What makes this difficult to invert as a whole is that this part here, we call it W here, right? This W, this and the U, they are not, these W's, they make it a little bit hard to invert the whole matrix. But there is a very beautiful trick in linear algebra, and it's called the Schur complement trick. And that allows us to invert this matrix more efficiently. And I remember that Schur complement trick in my linear algebra class. And it was one of these examples that I found completely useless, right? because I didn't know what it was good for. And here it turns out it becomes very handy, right? I don't know if Schur realized how important this strategy was when he developed this trick. What he showed is if you take this matrix, this one here, UW, this whole equation basically, and you left multiply with this invertible matrix. Don't ask me how he found this, right? But let's take this matrix and left multiply. What you end up with is this equation system. And it is in fact equivalent to the original equation system, because this is an invertible matrix, so you're not changing anything about the solution. But what's notable is this zero here. That's the crucial thing. There is a zero that appears here. So this matrix multiplied by the updates in camera poses and landmarks is this vector. And so we can equivalently solve this equation. And the matrix S that we have here is given by U minus WV inverse W transpose. This matrix is called the Schur complement. It's a matrix that is symmetric, positive, definite, and block structured. But as I mentioned, the key thing is that you have a zero here. What does that mean? It means this first equation, right, S times delta xp plus 0 times delta xl is this here. We can solve this for the update in the pose parameters without needing the landmark parameters. They are killed here by the zero, right? So we have one equation that's only for the camera pose updates. It's much like in the 8-point algorithm. Remember, we decoupled it into a problem that only involved the camera transformations. Same idea here. For the update in the camera parameters, we don't need to know the update in the pose parameters. We've decoupled it with this trick. And what's beauty is that this is an equivalence transformation, so the solution in the updates is still the same as for the previous problem. So we can go ahead and first compute the update in the camera poses, and once we, by the first equation here, and once we have delta xp, we can compute the corresponding delta xl from the second equation. And in fact, this basically means that we have to invert the matrix V. And remember, V is big, but it's essentially diagonal, so it's easy to invert. So we can basically back substitute the solution for delta xp that we get from the first equation into the second one. We know delta xp. We can bring that to the right-hand side, and what we have is V times delta xl is something on the right-hand side. And so delta xl is just V inverse times whatever that is on the right-hand side. So that's easy. The key challenge now is to solve the first equation, and this is this equation. S times delta xp is this thing here. This equation is called the reduced camera system. It's an equation to update the camera poses that doesn't require the update of the landmarks. And what it requires is for us to invert that Schur complementary matrix S. And that is in fact the key computational bottleneck in bundle adjustment, is to solve this reduced camera system. Yes?
What does BP and BL?
BP and BL is from here. This is basically, I didn't write it out, but if you take this loss function and set the derivative to 0, you get a linear equation system, right? This is a loss function, and that is a function of the update parameters, delta xp and delta xl, right? And then we want to minimize this in delta xp and delta xl. And we do so by setting dE by dx, p and l must be equal to 0. And since this loss function is quadratic in these, this equation will be a linear equation and it will be of this form. You can do this at home. You can actually compute the derivative of this with respect to this vector delta xp delta xl, and you get a linear equation system, and then you'll know what bp and bl are. I didn't write them out here, but you can do that at home. So it's constant. The unknowns are these, and these are all constants. Okay, so far so good. This is the reduced camera system, and that is the key bottleneck in bundle adjustment. And for decades, people have been solving this reduced camera system by numerical solvers like conjugate gradient methods, for example. But what we found out, and I would have thought the bundle adjustment problem has been around for 100 years, is definitely a solved problem. Well, it happens in research that you think something is solved until someone comes by and proves you differently. And one of my students, Simon Weber, who actually did the exercises, I think last year or the year before, he looked, and maybe through this class, he studied bundle adjustment, he looked into it, and he said, this is not how you should solve this equation system. And he introduced last year at the CVPR conference a paper that he called power bundle adjustment. And this is a technique to solve this reduced camera system, this equation here, to get the pose updates in a way that is much faster and much more accurate and much more memory efficient than existing methods. And I decided, since this is a completely new way of solving the bundle adjustment problem, I thought this is a good time to teach this in class. So I've never taught this before, but I think it's a very powerful technique to solve it. And I think it will become the established way to solve bundle adjustment. And it's all based on something that you might remember from analysis. It's called the geometric series. It's a power series. So if you take an element r, scalar between -1 and 1, and sum up all the powers of r, then from 0 to infinity, if r is in the interval -1 to 1, you get 1 over 1 minus r. This looks maybe a bit weird, but I'll give you an analogy. This is something I often tell my children. They love cake, right? And I told them, here's a way that you can make sure that you will always have cake for the rest of your life. You just take a big cake, right? And every day you eat half of it, right? And you just keep doing that. On day 1 you get half a cake, on day 2 you get a quarter of a cake, etc. And it turns out you can eat cake until infinity, right? And the one cake is enough, right? And this is in fact what you get if you take r equals 1/2 here. 1/2 plus 1/4 plus 1/8 plus 1/16, etc. Well, what does it give you? 1 in total, right? And if you start at 0, then it gives you, then you get r to the power of 0. You get 1 first, then you get 2 here. And you can do that not just for 1/2, but for any power, for the powers of any fraction. 1/3, whatever. And this is called the geometric series. One result from analysis that I remember and that I really liked about my analysis class, how you can sum up infinitely many terms and still end up with something finite. What I didn't learn in my analysis class, and what I learned from my student Simon Weber, he's a mathematician, he pointed out the same series applies for matrices. So if you have a matrix, that matrix M, quadratic matrix, that is bounded, as we say, M is smaller equal to 1, basically means the largest eigenvalue is bounded by 1 and all the eigenvalues are M are bounded by 1. If that is the case, then 1 minus m inverse, the same that you have here, right, can be expressed in a power series of that matrix. So you have sums of powers of the matrix M plus some residual, and that residual is the remainder, basically from m plus 1 to infinity of that series. And the property is that this residual goes to 0 if you take m going to infinity, which means if you take the sum to infinity, you get equality here. This residual disappears, thus larger with larger values of little m. So basically little m is the truncation. You take a sum of powers and you truncate somewhere. And so you can approximate this 1 minus m inverse for a matrix. M1 is the identity matrix, by the way. 1 minus m inverse you can approximate by a power series. Now you might say, what is that good for? Well, first of all, it's pretty beautiful that you can do that for matrices. But we'll use this power series to approximate the Schur complement, the inverse of the Schur complement. Because remember, what we need to do here is we need to invert S. And we need to somehow compute the inverse of S, and we can find an approximate solution. So this S, here it is written again with these matrices U, W, and V. That's what S was. If we pull out the U, then we get U times identity minus some matrix here, right? And so S inverse, if we formally write it out, is this matrix 1 minus this thing inverse times U inverse. But U, remember, was a small matrix, so that's easy to invert, and it is block diagonal. The key difficulty is then therefore inverting this. And what we can do is we can now apply this result from the geometric measure, from the geometric series for matrices, in order to approximate this thing here with a power series. And this is what we do here. So this thing, if we go back here, we have the matrix m to the power of I summed from 0 to m. And in our case, the matrix M is this matrix here. So we take this matrix, here it is, take its powers to the power I, sum it up over M, and then we have the U inverse that we retain from here, and that gives us an approximation of the inverse Schur matrix. Yes? Mm-hmm. So here's this matrix in that Lurakis sites, and you see V is block diagonal, but note that U is also essentially block diagonal, right? This is U, and U is much smaller, so that's much easier to invert. To what extent the structure is like that, interestingly, depends on the type of, it's a good question that you're asking. To what extent this matrix structure really looks like that depends on the kind of bundle adjustment problems. In the sense that if you have a bundle adjustment problem where you have one 3D structure and the cameras are all surrounding it, then you have a setting where any given 3D point is visible in potentially every image, right? Or many images. If instead you have a scenario where you move with the camera through a room and you face forward, then points will disappear from the various images and they will not be visible in all images. And so the neighborhood structure governs the structure of this system matrix. But here, in many cases, it does look like that, and then you can make use of the fact that U can be inverted fast, and so we can just compute the inverse of U, and the rest of the Schur complement we can approximate by this power series. Why are matrix power series a good idea? Because you don't have to invert matrices. you just multiply matrices. And multiplying matrices is something that modern computers can do very fast. In fact, computers and the software libraries were designed, the whole MATLAB revolves around making matrix multiplications fast. So this is something that is easy, and we can do that to any order, and we get a better and a better approximation of the inverse of the Schur complement. And so this is fast and numerically very stable to do. And so we can compute the landmarks, the poses much faster by solving this inverse Schur complement with the power series, and hence the whole problem can be done much faster, also much more memory efficient, because you can multiply these matrices in place, so it doesn't take much memory. And we actually did evaluations in last year's publication. Here's, for example, 2 well-known bundle adjustment problems from a data set called BAL. The BAL data set is called Bundle Adjustment at the Large. It's a popular data set of bundle adjustment problems. And what we plotted here is the runtime and the loss, the bundle adjustment loss function. And as we said, you want to minimize the loss, and so you want to look at how fast can I minimize it. And you can see, depending on how much precision you want, these power bundle adjustment solvers, no matter whether you take a 64-bit or a 32-bit implementation, they are very fast. And both implementations give you essentially the same performance. Whereas existing solvers, this is a technique called square root bundle adjustment, and this is the commonly used Ceres solver, is much slower. In fact, if you take this cutoff and say, how long does it take me to reach this energy level of the loss function, here we're talking about maybe 1 second or something like that, whereas here we're talking 6 or 7 seconds, or maybe more, right? So it's almost, you could say almost an order of magnitude faster than the state of the art. And similar on this problem, right, where the Ceres solver takes some 23 seconds and ours takes some, 4 seconds. Why is it important to look at 32-bit and 64-bit implementations? Nowadays, you would run a lot of these on graphics hardware, on GPUs. And GPUs typically work in floating point 32-bit. So you always need to check for numerical algorithms whether the performance is the same or similar if you only have 32-bit implementation. Because if it is, then it means you can run this straight away on a GPU and get a dramatic speed up. Now this is just for 2 bundle adjustment problems. What you'd like to see is, does that really hold for all conceivable bundle adjustment problems? The BAL dataset contains approximately 100 bundle adjustment problems. And what we did is we averaged all of these 100 problems into one single plot. And basically we said, how long does it take to solve it exactly? And that is then considered the unit of time. And then we can normalize everything to that same time unit, which gives us what we call a relative time here. And here's the number of problems that we are able to solve in this relative time. Again, and in this plots, you want to be in the top left corner, meaning you want to solve as many problems as possible from these 100 problems in as short a time as possible. And then obviously we terminate at a certain tolerance. Tolerance are these thresholds where we say, okay, this is good enough. This is the accuracy we want. And then you have low tolerance. That means you solve the bundle adjustment to low accuracy. And then you have high tolerance and you have very high tolerance levels, right? And what you see is this power bundle adjustment, these orange and blue curves, they do dominate the performance for low and high and very high tolerance. Only at extreme tolerance at some point, this approximation is no longer the fastest. But in practice, you typically don't care about super high precision when you solve these bundle adjustment problems. In fact, what is conceivable, obviously, is that you solve the bundle adjustment problems with power bundle adjustment up to a high tolerance, and if you want extreme tolerance, you can then run a classical solver on top of it. Sorry, I say high tolerance, I mean high precision. That amounts to small values of the tolerance tau. Yes? Yes. So this is a good point. It's a very good point. I note you really follow closely. We have this truncation here, m, right? And the higher we take m, the better the approximation. But obviously there is a trade-off. If you take higher values of m, the compute time will go up. And so you have an interest of taking m that is sufficiently high but not too high. And in fact, in our publication in 23 last year, we actually show an automatic way to determine m that is quite reasonable and that works quite well. And so all of the evaluations are done by this adaptive choice of m. And so I do believe, since we are significantly faster, and not only faster but also more accurate, right? So we get, even if we let runtime go very fast, far, up to 5, we're still better than some of the other methods. Here, for example, the 64-bit version still supersedes all the other methods. And so it gives you more speed and more accuracy, and also more memory efficiency. What I'm plotting here, or what we plotted here, is depending on the size of the problem, the number of observations that can go into the millions, like 1 million, 2 million, 3, up to 5 million observations, points observed in images. And what we plot on the y-axis is the memory footprint of the different methods for this size problem. Obviously, the bigger the problem, the more memory you need. But note, the orange and the blue curve are again the power bundle adjustment. And you can see here, we have significantly less memory than the competitors. In fact, 5 times less memory than the fastest competitor, square root bundle adjustment, this one here, and 2 times more memory efficient than the popular Ceres solver. And very often for large-scale bundle adjustment problems, maybe you don't care about runtime because you have time, because you can run it overnight. But memory can be the bottleneck, because your machine will eventually run out of memory. Once you go into 12 gigabytes, you have to find the right GPU to actually handle this, right? And if you want to solve even bigger problems, then at some point you're limited there. And so the key bottleneck for solving very big bundle adjustment problems is in fact the memory. And having something that is twice or even 5 times more memory efficient is valuable. Yes? That's a good question. How sensitive are they to initial conditions? This is an important problem. And in fact, there is a follow-up paper that's in the making, that is under review and that is not published yet, where we tackle exactly that problem. So if you're all asking very good questions, I'm impressed. If you're interested in going in this direction, doing research in this field, this is very much active research that Simon Weber and others are working on. And they introduced a new method that they called power variable projection, and that is a technique that is more independent of initialization. And because bundle adjustment problems, solvers need to have some initialization. So to summarize, in fact, I don't think I mentioned it here. Very often, what you do for these kinds of large-scale reconstruction problems is that you initialize with something not like the 8-point algorithm, but there is an extension or a variation called the 5-point algorithm that was published a few years ago. I don't know, 10 years ago, maybe more. And typically you would initialize with the 5-point algorithm and then run bundle adjustment after that. So to summarize, bundle adjustment was pioneered over a century as a technique to estimate structure and motion, minimizing this weighted nonlinear least squares problem with the residual squared. And then there are iterative solvers like Gauss-Newton, Leeuwenberg-Marquardt, but in the end you have to solve, you can deploy the Schur complement trick, then you have the reduced camera system, the problem in your camera pose update, and for that we advocate this technique called power bundle adjustment that is faster, more accurate, and more memory efficient than existing solvers. Let me briefly show you some examples. These are some papers that contain examples. This was a paper that became really popular. Snavely, Seitz, Zelinsky, modeling the world from internet photo collections. Basically what they did in these papers is they took this far enough so that you can enter the search term Notre Dame, and the algorithm will collect images from the internet that contain images of Notre Dame and will reconstruct then parts of the facade of Notre Dame, which is quite amazing because it shows you can reconstruct the 3D world without a camera, because the 3D world is in the images in the internet. And we are still kind of struggling at this point how to make this vision more scalable, that we can reconstruct worlds seen in images, seen in YouTube videos, for example. But this is one step in this direction. This is another complementary technique called parallel tracking and mapping, where we estimate camera motion and 3D structure in real time. And I think next time I'll show you videos, because I see that I'm over time and I don't want to take too much time. So I'll show you nice example results next time. Sorry about not showing them now, but we'll do that next week. Thank you. Okay, welcome everyone to class, Multi-View Geometry. This is Chapter 7, Bundle Adjustment and Nonlinear Optimization. And the aim was to tell you how you can jointly estimate camera motion and 3D structure from a set of points observed in a set of images. And remember here we had little m images and little large n points in each image. And then we basically have a perspective projection of the point xj here, rotated and translated into the camera eye, and then perspectively projected, and that should ideally match the observed point in the respective image. That was the idea of bundle adjustment, and then you have these variables theta ij, which are basically telling you whether the point is actually visible in that image or not. So, when you move around with your camera and you observe points, not every point will be observable in every image, right? And so this is the idea that here we can basically, have a variable that we set to 0 whenever the point is not visible, then it doesn't affect the whole estimation. And the whole point of this approach is to say, find the motions of the cameras for 1 through m cameras and the 3D locations of these points, such that this projection error is minimized, such that everything is maximally consistent, in the sense that the projected points end up where they are observed, ideally. This is the whole idea of bundle adjustment. as a problem, as an optimization problem. It falls in the class of so-called nonlinear least squares problems, which you can see because you have a sum of squared expressions, but each residual depends on your unknowns in a nonlinear way. If this residual inside the square was linear in the unknowns, then it would be a linear least squares problem. Then the cost would actually be a simple quadratic cost that is easy to minimize. But as soon as this residual becomes nonlinear, you are facing a so-called nonlinear least squares problem. And then we talked about different algorithms to solve these problems. We talked about the Gauss-Newton algorithm, damped versions like the Levenberg-Marquardt algorithm, and lastly we talked about power series approaches like the power bundle adjustment that give you a much faster, more accurate and more memory efficient solution. And at that do I really want to switch off? No, I don't want to. No. Hey. Sorry. For some reason the system decided it wants to switch off. No, we don't want to switch off. It's not done yet. That's where we left off last time. And then I promised you I would actually show you some practical results, right? Because a lot of classes are generally about theory, about the mathematics behind it. But of course I know that the audience likes to see results, not just theory. So here are some results, and maybe to give you a bit of an idea of where this all stems from. The idea of reconstructing from camera images is a long-standing one. As I mentioned, the bundle adjustment problem has more than 100 years of history. Over time, researchers developed solutions that would allow you to reconstruct a 3D object from a set of images, but very often these solutions were obtained in controlled environments where you have your own camera, you can calibrate it, you can compute the intrinsics, you can move it around, you can determine the motion, you can do everything step by step in a very controlled way. The result being that the world is full of images, but no one can use these techniques unless they're really an expert. And the key problem of computer vision is that computer vision in general will only become a commodity once the public can actually use technologies, and once you don't need to be a real expert to run a certain method, right? Because a lot of this, if you don't know how to implement a Levenberg-Marquardt algorithm, then you will not be able to solve this stuff. And if you don't know how to calibrate your camera, because all you have is a smartphone and you don't know anything about intrinsics, then you can't use this, right? But then came a time when people realized, can we not make this accessible to the internet? And this is a technique that was pioneered by 3 authors, Noah Snavely, Rick Zeliski, and Steve Seitz. And they're all still very active. I saw all 3 of them at the CVPR 2 weeks ago. What they published in 2008 was a paper called Modeling the World from Internet Photo Collections. And the key idea in this work was a somewhat groundbreaking one. They said the internet is full of images, either on Google or on Flickr or whatever data set you want to use. Tons of images are there. Can we put in a search term like Notre Dame, get all these images automatically in no time? And is that sufficient to reconstruct a 3D model of Notre Dame? And so this goes well beyond having your own camera and calibrating it and taking the images in, meaningful distance from at the same lighting conditions, right? You enter Notre Dame, you get all sorts of images. Some taken at day, some taken at night, some taken close-up, some taken far away, some possibly paintings of Notre Dame, right, that look completely different from the real one, right? So a lot of the effort in this paper goes into what you would call pruning. They first go through all these images that Flickr spits out and go through and check, do they match my requirements? And one of the things you can check nowadays is, does the image contain the camera intrinsics? Very often they are stored with the image. If they are, good. If not, kick the image out, go to the next one, right? And so they only retained camera images that were in some sense meaningful. Next, they went ahead and checked, is the color consistent across these images? Because if some images were taken at day and some at night, things look very different from day to night. And then it's very difficult to automatically find any kind of correspondence. Rather than trying to find the correspondence, they said kick out any image that isn't color consistent. So they pre-process very aggressively and just prune out, and it all builds on the assumption that you have enough images. And I think for the internet that is a valid assumption. The internet always has tons of images. Like here, for example, you see the window of the Notre Dame, but pictured from the inside. That's not going to help you when you try to recover the facade of Notre Dame, right? You have to make sure you actually have the same structure. Or here you see images where it's predominantly a selfie of someone with a tiny little bit of Notre Dame in the background. That's pretty useless to recover the facade of Notre Dame. And here is a person that I don't see what Notre Dame's got to do with it. It's probably a picture of someone taken inside Notre Dame or something like that. So you see there's all sorts of images that come up that have very little to do with what you need, but there is enough that you can make work. And then they showed that indeed just typing the search term, the algorithm can prune out, get enough images in order to recover this kind of reconstruction of the facade of, oh, I think this doesn't match. This looks like the Trevi Fountain to me. I don't think it's Notre Dame, sorry, this is but some reconstruction of the Trevi Fountain is something that was popularly reconstructed in Rome, not in Paris though. Yeah, I think that's more the Trevi Fountain. Well, it doesn't matter. So you can, somehow take all these images and get a reconstruction, and you see all the camera positions were being estimated as well. So this is one way of deploying bundle adjustment in order to get large-scale reconstructions based purely on internet imagery. But I should say it's not just bundle adjustment, there is a lot more. There's pruning, there's finding the right images, there's identifying corresponding points, and once you have the points, then you can do the bundle adjustment. Another interesting work that inspired a lot of research in our field is a work by Georg Klein and Murray that is called PTAM, Parallel Tracking and Mapping, for small AR workspaces. So this was a paper published in an AR conference called ISMARS, the International AR Symposium, Mixed and Augmented Reality, International Symposium on Mixed and Augmented Reality. And I suspect this may have been one of the most influential ISMAR papers ever. ISMAR is not like as big as CVPR or ECCV. It's a somewhat smaller event, but this paper had quite an impact. Technically, I talked with Georg Klein. He was at our workshop at CVPR 2 weeks ago. And he said that there's not necessarily so much that was novel in this work, but it was integrating a lot of techniques in a system that ran in real time. And this, I found, was quite amazing, and it really propelled a lot of research in our lab. And I'll show you some examples now from these works. So here is a video of this multi-view reconstruction of Dubrovnik. So these are reconstructions achieved from a set of camera images. And you see the reconstructions are not dense, they are sparse point clouds. And you always see these camera locations where the many images were taken. And you see you can reconstruct the whole town of Dubrovnik using the search word Dubrovnik and all the images that come out. It always reminds me that I've never been to Dubrovnik and I should really go there at some point. Okay, sorry, this is... And here is another one. I hope the video plays. This is Rome. There was a paper with a fascinating title, Building Rome in a Day. You know, this expression, Rome was not built in a day. What they did is they actually, in that paper that appeared a few years back, they showed how much of Rome you can reconstruct within 24 hours. But this was using intensive amounts of cloud computing, and so there was a follow-up paper with an even nicer title. It was called Building Rome on a Cloudless Day. And I thought that, you know, you can hardly beat the first title, but you can. It's, you know. So these were all reconstructions then achieved on just a single PC with one graphics card or something, right? And so algorithms have evolved to a level where you can scale them, but you see, you know, just the fact that it takes a day to compute all this shows you there is need for faster bundle adjustment solvers, which is why we now develop the power bundle adjustment. Here's PTAM. This is Georg Klein. Maybe something up front. Some of you may know the HoloLens project from Microsoft. This is the origin of HoloLens. Georg Klein and his PTAM is what really was the first version of HoloLens, was built on PTAM. Much like the Meta Aria glasses are very much built on the things we developed here. Yeah, so you see, it's for tracking and mapping in small environments. I'll try to play the video again. Here we go. 2007, and so you see what's happening here is it's all recorded live, so you see everything is computed in real time. It tracks points, it finds correspondence, and then you can see it estimates the 3D location, and you can check how accurate it is by this grid that is projected into the world, and while you move around, the grid seems to stay fairly static. This is a way to validate how good the tracking is. And that works so-so, because when you move away and come back, the grid is still there, but whether it's shifted in the meantime is something you can't really tell very precisely. But then once you have a technique that can track a single camera at fairly high precision and robustness, you can do tons of things. And this is what Georg Klein showed. He's an extremely creative guy, and I love these videos. You'll see why. So these were extra videos made in Kyoto at the ISMAR conference. Like outside the train window, he can, find this grid, and then he can superimpose, little objects that wave around in real time. So you see through the camera, and you see while the camera is moving, you can project things into the world. Lots of, entertaining things that you can put, right? I know actually some of the researchers that you see in the pictures. So this shows you can move the camera around and things stay fairly static. Or here, this is my favorite. I think he's a big fan of Star Wars. And so you have this called Ewok Rampage, I think he calls it. There we go. And this is the Stone Garden, and so while he's moving around with the camera, there's Ewoks and Darth Vader fighting each other. So it gives you a little glimpse of augmented reality in action, right? How you can, and this is very much what a lot of, propelled a lot of activities in the field of augmented reality. The fact that all of a sudden you could put objects into the scenes in real time. It led to the development of the Microsoft HoloLens. That said, I think the HoloLens recently got discontinued, so it will not be a product anymore. I've talked to the lead developer, Mark Polyface, and the issue is it's not so easy to commercialize this stuff. Right. It's a very heavy device. You put it on your head. We just talked about this with a new startup. No one wants a big head-mounted device on their head. especially not if you're at work, right? And so, supporting workers by putting a super heavy device on their head, it's just not, it doesn't really support them, and they don't see the added value. And so it's, although there is a lot of potential there, how to commercialize things is a whole different question. Just because the technology is cool doesn't mean someone's actually going to buy it. Keep that in mind if you do your next startup.